welcome back to the second part of the lecture on atmospheric circulation and wind. We're going to jump back into it and talk about different atmospheric cells. And so to understand this process, it's a good idea to first talk about what our atmosphere would look like if the Earth wasn't rotating. The rotation of the Earth tends to cause a little bit more complexity. So just analyzing it in this way is a good way to kind of approach it as an idealized scenario. So we can think if the Earth was not rotating, then all of the or the majority of the heat that the sun exposes to the Earth would be located near the equator. The equator would be the hottest region of the Earth, and because of that heat, the atmosphere there would expand, and you'd have a low pressure there, and that expanding atmosphere would rise, as you see here, and then that rising atmosphere would be pushed out in the upper atmosphere towards the poles, and it would be drawn in the lower atmosphere towards the equator. And so that poleward circulation in the upper atmosphere and the equatorial direction of the lower atmosphere creates this circulation pattern. In our atmosphere, where you actually have the Earth rotating, instead you have kind of these three different cells instead of that one big one for each hemisphere. The first cell, that first area of atmospheric circulation, is called the Hadley Cell. And that's between the equator and 30 degrees latitude. So there's the northern Hadley Cell, which is the equator to 30 degrees north, and the southern Hadley Cell, which is 0 to 30 degrees south. And that cell is caused by the same process, where you have the sun heating up the area near the equator, causing a low pressure system, which moves air upwards near the equator, and then outwards in the upper atmosphere, and is drawn in the lower atmosphere. That area of low pressure is an area that we call the ITCZ, the Intertropical Convergence Zone, because you have air that's converging at the equator. So you have air from the northern hemisphere moving towards the equator here, and the southern hemisphere here too. And so that convergence creates the ITCZ. And so that convergence also causes some strong winds to develop. As you can see here, these are the trade winds. And we call these trade winds in the tropical region the doldrums. They generally move from east to west. On the northern, or the more poleward end of the Hadley cells, you have what's called the Subtropical High. So as that air moves in the upper atmosphere, it eventually comes down, and that downward movement of air causes a high pressure system, and that latitude is called the Subtropical High. It's a high pressure system. It's also called the horse latitudes, kind of a bad story, just because the subtropical high is an area that usually receives very little wind, and so sailors could not travel as quickly when they're trying to cross the horse latitudes, and sometimes to conserve water they would have to kill off their horses. So instead we call it the subtropical high, and it's located at about 30 degrees north and south latitude, and it's formed by that falling air in that latitude region. Above that subtropical high, we have the feral cell, the mid-latitude cell here, which extends from 30 degrees latitude to 60 degrees latitude in both hemispheres. And in that cell, you have strong westerly winds. So as that air moves down at the subtropical high, it then spreads apart and either goes back into the Hadley cell or it goes poleward into the feral cell. And so as that air near the surface moves poleward, the Coriolis effect causes that air to move westward. And so you have the trade winds that are mainly moving from west to east, or westerlies. And so you have convergence occurring as the westerly winds cause the feral cell to push air towards the poles near the surface. And you also have the polar cell that's above it that has a high pressure system that's forcing air more towards the equator. So you have that the convergence of these westerly and the polar easterlies causing this convergence in here. And so the polar cell is located above 60 degrees, so 60 to 90 degrees north latitude and 60 to 90 degrees south latitude. And it's formed because the poles are very cold, and so that air sinks as it cools right in here. And so that sinking causes a high pressure system, and that high pressure forces air to move away from the poles, and that causes the circulation in here. Yeah. So we can see this in our actual weather. These are a couple different very cool websites that show the current wind patterns throughout the globe. And you can see in here, for example, you have this convergence of air right around the equator. And that there is what we can see of the ITCZ, the Intertropical Convergence Zone, as that air kind of converges along near the equator. You also see here this kind of isolated circulation pattern that is the feral cell, and that's also in the northern hemisphere as well. So we can see that while the real world is kind of more complex and you have different cyclone systems developing and all sorts of kind of complex things as well, that these three cells are a good way of describing the main circulation patterns within our atmosphere. So I will say also that our random statement for this week is dragons are purple. So dragons are purple. All right, so the next thing that we're going to be talking about is jet streams. So you can see here in red this jet stream moving across the northern hemisphere. And a jet stream is just a narrow band of fast-moving air. And you generally get them whenever you have a convergence of air. For example, that subtropical high, you have air converging from the subtropical regions as well as the tropical regions, and they form this subtropical jet stream. Even stronger is the polar jet stream, which is around 60 degrees north compared to the subtropical jet stream, which is around 30 degrees north. And the polar jet stream tends to be a little bit stronger, and it has those easterlies and the polar easterlies and the subtropical westerlies converge on each other, and they tend to create very fast-moving air. We just recently had a plane break the record for the trip between North America and Europe, just because it was able to travel along the path of this jet stream in here. So these jet streams always move eastward due to the Coriolis forces. So remember, as air moves poleward, it's going to be curved east, and as it moves towards the equator, it's get curved to the west. And so that Coriolis effect causes the jet stream to move in an easterly direction around the planet. And as it does that, it usually takes a fairly wavy path. And so the meanders of the jet stream are what we call Rossby waves. And so that would be this in here. These Rossby waves indicate that the jet stream, or the dividing line between the ferrule and the polar cells, is particularly wavy. And so you may have heard about the polar vortex. The polar vortex is just a weather phenomenon in which the jet stream is very wavy, and it allows cold air to move particularly far south. And so you can see here, if the jet stream is kind of straight, then this cold air mass of the polar cell is kind of confined to the more polar latitudes. But as this jet stream gets more wavy, this cold air mass gets pulled further down, and that can cause some really severe cold weather systems all the way down into the United States. We can quantify these Rossby waves by what's called the Arctic Oscillation. So this is just a value we give for how wavy the jet stream is, with fairly straight conditions having a positive phase and very wavy conditions with these big waves indicated by a more negative phase of the Arctic Oscillation. And a number of scientific papers have shown that the phase of the Arctic Oscillation has been related to a lot of different weather phenomena. So it's a good way of incorporating these into climate models and weather models in order to predict different weather events due to where we predict the jet stream waviness to be. And climate change is actually expected to increase these Rossby waves, the waviness of the atmosphere, as we change the temperature gradient in the planet, as we warm up the Arctic more than the poles, then we can cause that waviness to get increased. So we expect that more extreme events are going to be caused by climate change, in part because these Rossby waves are likely to increase. All right, let's take another break, and we'll continue on to the final part of this lecture in a bit.